We've been talking about the enthalpy of formation, and what I said was that the enthalpy of formation is with respect to a reference state 25 degrees C, 1 atmosphere. The symbol for enthalpy of formation, it's usually on a per kilomole basis, but that's the symbol that we use. So what we're going to do, we're going to take a look at an example of the formation of a substance, and that is carbon dioxide. So this is the system that we'll be analyzing, and what we can see is that we have on the inlet, we have a carbon stream and we have a diatomic oxygen stream. Both of those, notice, are at 25 degrees C, 1 atmosphere. And on the product side, so what's coming out of this vessel, whatever it be, it's a steady flow system, would be carbon dioxide, and again, it is at 25 degrees C, 1 atmosphere. And consequently, the change of enthalpy, and just normal enthalpy, they're all at the base state, 25 degrees C, so your products and your reactants. And we have heat coming out of our system. So what we're going to do, we're going to begin by applying the first law to the system. So that is the first law. Now to begin with, this is a fixed vessel, no moving walls, steady flow process. Consequently, there is no work, and we can cancel that out. It's not moving anywhere, so there's no kinetic energy, nor is there any change in potential energy, so we can neglect those components. So what we're left with for the first law is basically just the heat change is equal to the change in enthalpy of the product stream minus the enthalpy of the reactant stream. Now when we look at this, given that both the products and the reactants are at 25 degrees C, 1 atmosphere, what we see is that the only thing changing in terms of the enthalpy is going to be due to the breaking of chemical bonds or the formation of chemical bonds. So the only thing causing a change in the enthalpy I had mentioned between the products and the reactants is the enthalpy of formation, and that accounts for the change in chemical bond energy. So let's proceed and take a look at the enthalpy of formation for the products and the reactants that we have. So on the product side, we had carbon dioxide. And so if you go and you look in the table in the back of your book, you'll find the heat of formation, or the enthalpy of formation, I should say. And for CO2, that's what we get for CO2. Now if we look at the reactants, remember with the reactants what we had coming in, we have carbon and we have oxygen, diatomic oxygen. So let's look up the values for those two. So first of all, for carbon, we find it to be 0, because remember this is one of the substances or elements that I said was the basic foundation or building blocks for everything in our heat of formation or enthalpy of formation table. For diatomic oxygen, and so those are the ones that we have for a reaction. Now if you look in the table, you'll also find for diatomic nitrogen and hydrogen the same thing, where their heat or enthalpy of formation for both of those is also going to be 0 kilojoules per kilomole. So what does this mean? What it means is the above process that we were looking at, we have elemental carbon reacting with oxygen. That's the oxidation reaction, and it's characterizing actually combustion of carbon into carbon dioxide. And when you go through that combustion process, you have a heat release, and that is noted with the heat coming out that we see in our schematic there. So the above process represents oxidation of carbon. So what the process that we looked at represents is actually the oxidation reaction or the combustion of carbon. And what we will do, we will introduce another term, and that is referred to as being the enthalpy of combustion when you do have the oxidation reaction. And if we go back and take a look at our schematic as well as the heats of formation that we had in that picture, you'll notice first of all the heat release here is 393,520. Now let's take a look at the heat of formation for carbon dioxide. It's the exact same number. However, it's negative, and the reason why it's negative is because remember for a system we said heat leaving the system would be negative, and consequently it's accounting for the fact that heat is leaving. So the heat of formation is identical to the heat that we see coming out, and that's because what we have here is the combustion or the oxidation reaction of elemental carbon. So with that, what we can write is we can say that the heat of combustion, or the enthalpy of combustion, is minus 393,520 kilojoules per kilomole of carbon. And this is also sometimes referred to as being the heating value of a fuel. So if you were to take the absolute value of your heat of combustion, that would be equal to the heating value. Usually heating values will be expressed in terms of per kilogram, and so you'd have to include the molar mass in order to convert the per kilomole to per kilogram, but it'd be kilojoules per kilogram. So that is the heating value. I want to spend another minute talking a little bit more about heating values because they're fairly important and used quite often within mechanical engineering. So what we have when we talk about heating value, we can have a higher heating value, and it is given the symbol HHV, and you'll find tables with higher heating values. But this would be if the water vapor in the product side was in the liquid state. So what happens when the gaseous water vapor condenses into liquid? It goes through the heat of going through the phase change from the vapor state to the liquid state, and consequently what it does is it liberates more energy, and consequently that's why we would call it the higher heating value as it goes through the condensation process. And we also have a lower heating value, and it is given the symbol LHV, and that would be where the water in the product side remains in the gaseous state or the vapor. And so you can convert from higher heating value to lower heating value using a very simple equation. And the HFG here would be the heat of vaporization of water, and the number of moles of water that you would have. And notice the overbar, that's on a per kilomole basis. Final thing I want to say here is sometimes you're dealing with a liquid fuel instead of a gaseous fuel. So if you are dealing with a liquid fuel, So for example, if you're dealing with standard gasoline like you'd burn in an internal combustion engine operating on the Otto cycle, you have to vaporize that liquid first, and that takes energy to do so. And so we have a mechanism by which we can account for the heat of vaporization there when we go from the liquid state to the gaseous state, and we correct it with this relationship here. So depending on the values that you might have in your table may have the fuel that is going through the reaction, the enthalpy of formation for it in the gaseous state, and if you're dealing with a liquid, then you would correct it by knowing the heat vaporization for that particular substance or for your fuel. So those are the heating values, and it gives you an example of the heats of formation. What we'll do in the next class is we will apply it using the first law to a system, whereby we can then go through and do thermodynamic calculations using this enthalpy of formation.